early because we should all come down and check out the VR demo when we get out of class. Well, not till 11:30 because we have some more important people that we're showing it to at 11. But then we let the steerage come in and check check out, check out the VR stuff. All right, homework assignment was to calculate, well, set your binary tree up as doubly linked, right? So we can go back, and then also calculate depth. Okay. So let's do the doubly linked thing first. Okay, so here's our binary tree. So what we need to do is a binary tree. We'll add some other variables here, but it's going to keep track of a left tree, a right tree, and then also a parent tree. So we can get back to that. We're also going to keep track of our position, correct? Whether we are left or right. We already are. We're doing that. Where are we doing that?
Sharp.
Where am I missing it?
It's like line 4.
Line 18. Oh, that's LRR.
Yeah.
Okay.
I think in the second add method we made though, we would need to update.
I got you.
Yeah.
All right. So here's our add when we add a binary tree. So in here we're not actually updating that, correct? So so let's do that first. We'll bring this guy up to date. So if we do this to our left tree, we'll add BT, and then we'll go ahead and say BT dot position is equal to, do we just do,
LRR.
it's like char, capital?
Yep.
Actually, we wouldn't put it there. We would put it the other one, yeah. We'd let that other guy deal with where he ultimately lands. So if we placed him ourselves, we'll set it to L. If we placed him ourselves, we'll set it to R. All right, and then here's our other add. Oh, when we built the tree, we gave it a left or a right as part of the constructor. So in this case, we didn't have the left or the right. We're passing in a binary tree, so we don't necessarily know where it was. So we're updating its left or right. Okay, so now when we set something, we're also going to let him know about his parent. So not just are we setting the position for this binary tree, we're going to say BT dot parent tree is equal to us, right? Same thing here. BT dot parent tree is equal to us. That lets us climb back up if we need to. Okay. Then down here in our add, this dot left tree dot parent tree is equal to us, and this dot right tree dot parent tree is equal to us. I wonder why no language has used us as the equivalent. Us. Visual Basic used me, which actually makes a reasonable amount of sense. It's like the one thing about Visual Basic that makes sense.
Well, wouldn't us be referring to plural? I mean, usually if you say it's an object, it would be singular, right?
Well, now we do, demon possession type stuff, so it's Christian worldview. So, mean, that's the thing, right? You know, when they say us, and it's like there's
We
multiple.
are many.
Yeah, yeah. That was in some movie. I saw that. Like, there was The Exorcist. Terrifying movies.
My
Terrifying.
mom's boss did an exorcism.
Oh my gosh. Could you imagine? Well, you probably can't because you can't do the blade thing. You can't do the robo blade. Yeah, so I don't know, just synonyms for it. But so we'll set the parent tree for the right tree equal to the guy who said it. So this. Otherwise, we're passing the buck, and we'll let whatever tree ultimately finally places him, let him know that he's the parent. All right. So that's it for doubly linking our trees, right? Now we can, every tree knows about the tree above it. So that's not too bad. So, a couple lines of code, and we had that done. All right. So now, lastly, though, we need to give each tree a what is it called? Balance.
Factor.
The balance factor. Okay. So, and that's going to be an integer. All right. So balance factor. And when a tree is first born, it'll have a balance factor of 0. Okay. So that's when it first comes into existence. Okay, and this guy will set that. So we're calling upon our parent, the other constructor here. So we don't need to do it a second time in here. Just a quick question since we're sitting. Why does this line have to come first if we intend to use it? First of all, even though I mentioned it out loud, what does this line do? Because chances are you weren't paying attention. The line I have highlighted there, what's that actually accomplishing? What's it doing? Calling the other constructor. So this guy. We got two different constructors. How do we know that these are both constructors? Somebody other than the smart one. Well, you can answer this one. We'll give you each one.
Well,
And then we got to go to the steerage.
it's got the same name of the object.
Same name as the object, yeah. So constructors always match the name of the class, right? All right, so we have two of these guys. And for bonus points, what's that an example of? Polymorphism, okay. All right, so now, what's this line doing? Oh, she answered that. She said this is called the other constructor. Okay. So then my follow-up question was, why does this line have to come first? If we intend to call an alternate constructor to initially do some setup, the rule in Java is you must have that be the very first line in your constructor. You can have comments before it, but it must be your first logic line. Why is that? And I'll give you a hint. The answer is not just because Java said so. Why does that logically make some sense? What do we use constructors for? What's the purpose of a constructor? Okay, so give initial values to your object. Initialize your object, instantiate your object, build your object initially. Okay, so if we're calling upon the other constructor, we must be relying on that guy. We're kind of subcontracting the building of this object, right? Okay, so somebody hires me to build a house, and I decide, okay, well, I'm only going to do this part of the house, and I'm going to go ahead and hire out to have have the foundation poured or something like that. All right, so I'm going to have somebody else go and do some of the work. And why are we going to have them do that first? Why do we have to let them do that first? In real life, we could make the argument that, well, you gotta have to have the foundation poured before you start building a house on top of it. Okay? But we don't necessarily know the nature of what we're building here. I mean, there's certainly situations where if you, in real life, you might hire somebody to do the electrical. You might subcontract the electrical, and well, that's not going to happen until there's a house built up, right? Okay, so you'd actually do it in the opposite order then. But Java says this has to happen first. Why is that? What types of things do we do inside of constructors? What are we doing here? We're initializing a whole bunch of variables to some initial values, right? What are we doing here? Kind of doing some more of that, right? In fact, aren't we undoing something that was done up here? We are. So the idea here is that if you're going to rely on your other constructor to do something, you only get to do your specialized stuff for this particular constructor after he's done his initial stuff. Otherwise, this is kind of a roundabout example of coupling, right? This constructor is reliant on this constructor, and therefore we're going to let him do all of his stuff, even if we're going to choose to undo some of it or modify some of it after the fact, as opposed to us not necessarily knowing what's going on in here. And we set a bunch of values, and we trust that those are set the way we want. Then the subcontractor comes in and undoes half our work, and we don't even know about it until it becomes a problem later on. That makes sense? Okay, so Java says it is our responsibility to know what's going on in here, or to, at the very least, dictate what we definitely want certain values to be after the fact, after that guy does whatever he does. Okay. So we set our balance factor to 0. This constructor, when we call this guy directly, this is for when we build our initial empty tree. Looks like that. Otherwise, when we build other trees, we go ahead and partially use our other constructor. So that balance factor is already being set in here. We don't need to reset it to anything different in here. Make sense? Because we're not taking it as a parameter. All right, so now how do we calculate the balance factor? What's the formula for the balance factor? And there's 2 different correct answers. You just need to make sure you always use the same formula. Okay, so what was the formula we talked about last time for calculating balance factor? Did you do the homework, Van? You did the homework. Okay, how do we calculate balance factor?
So,
what is the balance factor? Let's start with that. What's the balance factor of a binary tree? Yeah, difference between left and right. All right, that's our balance factor. So how would you calculate the difference between the left and the right? We're going back to like when how far back we go? This is like 2nd grade math? Earlier, 1st grade? You got it? You didn't pass 1st grade.
don't remember that for sure.
So I have 2 values. I have the number 3. I have the number 5. What's the difference between 3 and 5? 2. How did you figure that out? Okay. Specifically, which math? What did you do? And actually, this is going to be the backwards answer, but it's okay. You took this guy and you subtracted this guy from it. All right. So the balance factor is calculated by taking the way we advertised it last time, the depth of the left side minus the depth of the right side. And we're not taking absolute value or anything, just taking those values, right? So you might get a negative number, and that negative number tells you kind of which side it's heavy, right? You might get a positive number, it tells you which side, it tells you that the other side is heavy. All right? So when would we actually calculate the balance factor for a node? Or for a tree? At what point are we able to calculate the balance factor for a a tree. Okay, when a tree is initially added, won't its balance factor always be 0? Don't answer so quickly. What are some different circumstances under which we might add a tree? You got stuff hanging off of it, right? Now, that'd be hanging onto a tree, but it's got a whole bunch of stuff, and we can't shake it off. Okay, because these are permanent bonds that we've created here. It's a chemistry thing. And since we're stuck in that first grade math, it's going to be tough. All right. So, I mean, we can't necessarily assume that the balance factor is 0. Certainly, brand new, fresh trees, right? Their balance factor will always be 0 before we've kind of hung anything else on there. But the reality is after we've added something to our top level binary tree, don't we have to recalculate the balance factor for everything? I mean, we can't just, we certainly can worry about where we just hung something, right? We just hung this tree down here. Whether it was a brand new tree with no children or, it was a giant tree. So we definitely need to look at that and see did something change. But the reality is that guy probably didn't change, right? Because we just hung him. So everything from there down is the same as it was a second ago. But we modified depths of stuff above us. So really what we need to do is after any add, we need to go back through and recalculate the balance factor of every tree in our tree because they potentially changed. Now, we could optimize that to an extent. We could say, well, I know I added this guy to the left, so the only place where the depth may have changed would have been to the left. But you probably should do that like a production type of situation, okay? But since we like to practice recursion, we might as well go ahead and get the depths of both sides. We already have a function for that, right? And we have a function that gives us the depth of a tree. And then we just do our math. We do the math stuff, and we take this guy and we subtract from it this guy, and we get a depth. And we're already doing that, I think, in our is out of balance or something like that. So now we're just kind of turning that into an actual number, right? Okay, so where would we actually make that call? We've completed an add. All right, so we hit the button, we say add something gets added on. Now we're happy. At this point, we clap our hands, everything's happy, we've added it. Now everybody knows about their parents, right? So if we needed to climb back up the tree, we could. It would be at that point in time when we've returned back to the program, when we have access to the top level tree, where we can point at the tree and says, okay, I've successfully added something. Our adds return Booleans, right? The tree has changed. Okay. The top level, I don't necessarily know how it changed. We could certainly add some abilities in here that might give us a little direction, but the tree has changed if I get a true back from that. Therefore, I need to go ahead and tell the tree, I need you to ultimately we're going to tell the tree to rebalance itself. But first thing we need to do is tell the tree to go ahead and recalculate its balance factor for it and all of its subtrees. Make sense? All right, so we need to teach a tree how to calculate his balance factor. So public, and we'll say void, because we're just setting an internal variable, right? I mean, if you really wanted to return it, you could, but so we'll say public void calc balance factor. So we're telling this particular tree to calculate his balance factor. And his balance factor will be the depth of the left minus the depth of the right. And if the right is null, what's its depth? 0. Okay. So this will give us an opportunity to kind of show a cool thing. I think I've mentioned it before, but this is one of these like kind of rare-ish things. Inline if statements. Did I mention that in any of the classes you guys have had? I'm guessing you've seen them.
We use them all the time.
Okay, yeah. All the time?
Fairly often. Actually.
Really?
Well, I do a lot of client-side development, so there's a lot of times where we're checking if something's null, and if it's not, we're setting it to a.
So exactly what we're doing here.
Pretty much, yeah. So we use that a lot.
I got you.
Not so much on the server side.
Why would the depth reset at 0? Or set at null, sorry. Is it worse?
No, not the depth.
Oh.
If your right child doesn't exist, the depth of that side is nothing. Okay, I don't want to subtract 5 from null. I mean, that might actually work for him with the math deficiency. But like, whoa, 5 minus null, it's bananas. No, I mean literally bananas. I was in a math class one time. I may have actually mentioned this before. This was funny. I was a lot younger, and I think I was in high school. And my it was those word problems, and it was something like apples and oranges or something like that. I got the right mathematical answer, but I switched fruits. So, I think it was like, you have so many apples, you have so many pears, something like that. I gave my answer in terms of oranges. The teacher took points off. I mean, that's like losing points for the going too long. I had all the math was right. I just switched fruits.
Is that without realizing, or did you do that?
Well, I would like to say without realizing. No, I guess I'd like to say it was on purpose, but I don't recall. So I'm pretty sure it was just the brain part. I zigged when I should have zagged. This is similar to the losing points for going too long when the teacher never told you what to do. Well, I guess in this case, they did give me the fruits. But maybe I was allergic to apples or pears.
That's one of those mistakes where they just like put smiley face.
Right, exactly. But all my math was right. He took off full credit. I lost all the points on that for switching the fruit. Yeah, it was bad. This was, I think it was when I was a freshman in high school. This guy was mean too. That was like, when guys, your voices are starting to change and stuff, right? It's like my voice cracked in class or something. He made fun of me. Now I'm like 9 times that guy's size. But I was probably 3 times the size then. All right. So calculate balance factor. We're going to go ahead and get the depth to the left. So int left depth is equal to, it's either going to be the depth of our left tree, if we have one, or 0. All right, so this is where this inline if statement thing comes in. Now, you never, ever, 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 ever have to use these if you don't want to. It's just sometimes handy in situations like this where we want this guy to get set to a value, and the value is going to be one of 2 things. So we're gonna write a Boolean expression first. So we're gonna say this dot left tree, if it's equal to null, or we could have said not equal to, depending on which one we have first. Put a little question mark there. This comes back from the old C. So this is again evidence that Java came from C. All right. So if the left tree is equal to null, we want this guy to boil down to a 0. Otherwise, we want, was it get depth? We want to get our left tree's depth. So that's the syntax for an inline if statement. So if I put a little comment here, this is Boolean expression followed by a question mark, true val, false val. The colon in between. Make sense? All right. You never have to ever write one of those if you never want to. Sometimes they're handy because this, we did something in one line that, really this is a lot of form validation type stuff, or value validation, I guess. Int right depth will equal to this dot right tree. If that guy is equal to null, return 0. Otherwise, go ahead and get the depth of our right tree. Okay. So when those two lines are done, we'll know that we have the left and the right depth. Make sense? Okay. Now we need to set our balance factor. This dot balance factor is equal to left depth minus right depth, like that. Okay. So now I have the balance factor for this guy. What do I need to do next? Okay. Potentially, depending on how you're doing this, that would be a really horrible way of doing this. Well, okay. Think about when we initially make this call. If I'm telling my binary tree, I want you to recalculate your balance factors. Okay? Basically, tree, update yourself. I'm starting at the top. So the very first time in here, this is the top guy. He calculates his balance factor based on the difference of this side and this side. Then what would he do? If he had a left child, he would tell his left child, calculate your balance factor. He would tell his right child to calculate his balance factor. That make sense? Balance factor is different than depth. It's done in terms of depth. And we certainly could optimize this if we, decided to throw some different additional pieces of information in, because presumably we have calculated balance factor for our various subtrees at some point. And if we just added something to the left, the right has not changed, presumably. Unless what's happened? If we had a rotation, potentially the right has changed. So, depending on the amount of information you want to keep track of, that kind of tells you, do you need to waste time recalculating balance factor for one side or the other? For us, from an accuracy perspective, we'll just tell everybody, rebalance your, redo your balance factor.
Couldn't we start at the bottom and just tell everybody to keep on their current if they? That's how I was doing this.
Well, you could, but the problem is, so what's the bottom? The guy you just added?
Okay. Yeah.
Okay, so I'm the guy we just added. So now you climb to the top. At what point do you traverse back down? Yeah, so I mean, I don't. It's not impossible, but I think the logic for that would not be easy. Yeah, so I mean, this is pretty easy. There's a couple if statements and move on with life, right? Okay, I got my balance factor. Now, if I have a left child, get to work. If I have a right child, get to work. I'm done. So, if this dot left tree is not equal to null, okay, if I have one, then we'll go ahead and say this dot left tree dot calc balance factor. If this dot right tree is not equal to null, then this dot right tree dot calc balance factor. That makes sense?
When you're saying depth here, you mean like how many levels it goes down, right? Okay. Because the book was referring to that as height, so I was confused.
Oh, yeah, I gotcha. Yeah, height and depth. I've always called it depth.
Yeah, they were saying how they always referred to it as the depth was what level it was in. So if it was 4 ways down, the depth was 4. And I mean, the furthest down node would have the same height and depth. I don't know how to explain. The tree would have the same depth as the lowest tree. If that makes sense. I'm trying to pull what I was trying to say into like words, but.
Okay, so a node itself has a depth, so it knows where in the global tree it lives. Whereas a top level, a tree from the top level knows its particular height. Okay, so if I go back to my, we'll have to modify the example a little bit because so we go back to my days when I was a flyer. The cheerleaders, I was always at the top of the pyramid. But assuming I was somewhere in the middle, all right? What? You don't believe I was at the top of the pyramid? And they had to get the whole team out there to do the catch, the basket catch, you know? It came crashing to earth. So the idea would be is that the pyramid itself, that tree may have had a height of 3. But my depth might have been 1 or something like that if I was only one level up off the from the top. Yeah, I can see that being reasonable. I mean, at the end of the day, don't worry about what they're called. Maybe it's more about what that information could be used for. Like how meaningful is that information?
When I looked at your depth method, that made sense. That it was actually calculating what I thought was height. So.
Sure. So if you're in a situation where knowing the height of a tree is beneficial and knowing the depth of a particular tree within the larger tree is helpful, then those would be 2 different pieces of information regardless of what you call them, I guess. But there probably is, back in the beginning of binary trees, the official name for them. And my guess is the book probably is using the correct ones. All right, so if we have a left tree, tell him to calculate his balance factor. If we have a right tree, tell him to calculate his balance factor. And now it's not our problem anymore. We've effectively made our pseudo-recursive calls, right? Told that we've delegated. Okay, we've delegated our tasks to the subtrees. That should be it. So that was the homework assignment. Calculate, be able to climb the tree, and then be able to go down to have the capability of going up the tree, and then having us the ability to calculate the balance factor of each subtree. Okay, let me check something here. All right, I've at least mentioned heaps in here, right? But they're effectively priority queues.
We used them in shunting.
Okay. Well, you didn't necessarily use them. Yeah, I talked about it then. Okay. So what we're gonna do here? Would any of you be horribly upset if we don't actually implement rotations? You weren't looking forward to that? Huh?
So I sort of was. I'm probably the only one.
Well, I mean, you can do it if you want, I guess.
I sort of started.
Okay. I mean, so my initial intention was to do the rotations over the weekend, but I got to leave in a minute because we're doing the VR demo, and next week's our last week before finals, right? All right, and I think it would be more beneficial for us to get through graphs for next week in terms of body of knowledge. All right, so rather than having you implement something over the weekend, I want you to read the entire chapter 5. Let's get all the knowledge in, and then we'll go through and talk about it next week. Specifically, Dijkstra's shortest path algorithm is going to be, that's a famous algorithm. So we want to make sure we hit that next week. So let's get all the knowledge installed, and that way we can kind of go through graphs at the high level pretty quickly, and then we'll talk about Dijkstra's shortest path for, there's a famous problem called the traveling salesman problem. We'll talk about it in terms of that. How many of you have heard of traveling salesman problem before? Sometimes it's just shorted TSP. It's a time complexity type of discussion where if you have a salesman, just the high level of this is, there's a guy who sells crap, and he lives in Grafton, let's say, and he has to visit 10 cities in the area, and here's the how long it takes to drive between those cities. What's the best way to visit all of these different places? What's the most efficient? way to visit all these different places if he ends up returning home at the end and that type of thing. And it ends up being a kind of a divide and conquer type problem, but it's you really have to try every combination. I mean, it's expensive to write that. So it's, if you only, a human being, if you only have 3 or 4 different cities you have to visit, you can kind of probably figure it out relatively quickly. But you can imagine as the number of cities gets larger and larger and larger and larger, how much it would take to calculate that. And now think about how GPS might work, your GPS applications, when they have to figure out what's the best way to get from, Mequon to Los Angeles via car. Think about all the nodes, all the little towns in between. It's pretty interesting, right? So let's talk about that next week. So no programming assignment over the weekend, but read all of Chapter 5. Sound good? All right. So, and like I said, if you're interested, and I hope several of you are, show up to the cafeteria somewhere between 11:30 and 1 and come check out the VR stuff. We're going to have all 4 systems set up with some cool games, especially Robo Recall for Oculus is just ridiculous. I do encourage you to play that game Littman style, though, where you don't use the guns. Instead, you teleport to every robot, grab them by the chest, grab them by the head, and rip their head off. And then throw the decapitated body at another robot to kill them. That's the way to really play the game. So, all right, I will see everybody on Tuesday.